Rotating frames and Coriolis force. Consider two frames S and S dash. S dash is moving with an angular velocity omega relative to S. Consider at time t equals 0, their origins and base vectors coincide. See the figure. Position vector of P are equal to I cap x plus z cap y plus k cap z for S frame, and I dash x dash plus z dash y dash plus k dash z dash for S dash frame. Since S dash frame rotates, unit vectors I dash, z dash and k dash will change with time, whereas unit vectors I, z and k will remain constant. When a vector changes, we may write dr equal to r sin theta d omega. And in vector form, we can write dr equal to d omega cross r. Differentiating with respect to time, we get dr by dt equal to omega cos r. Similarly, we may write di dash by dt equal to omega cross I dash, where omega angular velocity of rotation, dz by dt omega cross z, and d cap k by dt equal to omega cross k. Change of vector r when the frame S dash is rotating with angular velocity omega with respect to S frame is given by, this is the expression, dr by dt equals to I dash x dash plus z dash y dash plus k dash z dash plus omega cross r. So we may write dr dt for inertial frame equal to dr dt for rotational frame plus omega cross r. From this expression, the operator equation can be written as d dt equal to d dash by dt plus omega cross. By removing the r vector from the above expression and double differentiating with respect to time, we get acceleration. So a equal to a dash plus twice omega cross dr d dash dr dt plus omega cross within whole bracket omega cross r plus d dash omega dt cross r. Here a dash acceleration in the rotating system or frame twice omega cross d dash r by dt. This term is present only when the point r is moving in the rotating frame and is called Coriolis acceleration. Omega cross r is the centripetal acceleration. It is directed toward the axis and its magnitude is omega cross r omega square r sin theta, which is equal to v square by r sin theta. So this is the magnitude. D omega dt cross r, it is the acceleration produced by the angular acceleration of the rotating system or frame with respect to the inertial frame when omega is not constant. Assume that the Newton's law of motion holds in the inertial system, then ma equal to f. In rotational frame, Newton's law assumes the form. So this is the form. So in this form, let us put m d dash square r by dt square equal to f effective, and d dash r by dt equal to v dash. So that to an observer in the rotating frame, it appears as if the particle is moving under the influence of the effective force F effective given by F effective force equal to F minus twice omega twice m omega cross v dash minus m within bracket omega cross r bracket close minus m d omega dt cross r, where twice m omega cross v dash is called Coriolis force, and it is perpendicular to the plane containing omega and v dash. So this is the expression of Coriolis force.